Okay, so today we are studying the solution of the damped oscillation, damped vibration. Okay, vibration. Okay, so we get the solution on the last day is y is equal to c1 e to the power minus k plus root under k square minus omega square into t plus c2 into exponential over minus k minus root under k square minus omega square whole into t. So if in case 1, if k square is greater than omega square, so in this case root under k square minus omega square is real, that because this whole term cannot get in a negative, that means this term cannot become root under minus 1, that means this term is not become a imaginary one. So obviously this term always be real in the case of k square if the k square is greater than omega square, and obviously it is less than k, that means this exponential 2 term are real and negative. It means that the displacement of y of the particle is continuously decreases with time. That means, so obviously, so this term c1 exponential over minus, suppose that this is become a and this is become b, suppose, so minus at plus c2 e to the power minus bt. This is just for a explanation, this is not required for the solution actually. So that this equation shows that the exponential term, both two term is negative order, so that means it shows that the particle, the displacement of the particle along with the y axis, because we get the dimension for the traveling of the wave in along the y axis, it is so it is gradually decreases with time, it is continuously decreases with time, and such type of motion, so the such type of motion is called over damped motion. Clear? So such type of oscillation is called over damped motion, and it is shows like that, it is seen like that like that. Clear? With respect to time, the motion will be decreases in the respect to time. This is the first case. Okay, now we turn over the second case. So when for the second case, when just a minute. In the second case, if k square is much equal to the omega square, what will be happen in this case? So it is very much close to each other. So we consider in this case, when root under k square minus omega square is not 0, obviously, because it is very much close but not equal actually. But we write here that we write that in here a very small quantity minus, okay, h, get the term k square minus omega root under k square minus, so let h is equal to k square minus omega square. Is it clear? Now from this equation, the equation is, we have already have e to the y is equal to c1 e to the power minus k plus root under k square minus omega square into t plus c2 e to the power minus k square minus omega square into t. So we rewrite c1 e to the power minus k plus h into t plus c2 e to the power minus k minus h into t. Clear? We taken out this one minus kt, so in the between c1 e to the power ht plus c2 e to the power minus ht. Clear? So e to the power minus kt. Now we broken the exponential term in exponential order. 1 plus ht plus h square t square by 2 factorial 2 plus dot 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 plus c2 1 minus ht plus h square t square by 2 factorial dot 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 dot. So for e to the power minus kt c1 1 plus ht plus c2 1 minus ht neglecting the higher order term. We're neglecting the higher order term. Now we get this one. So e to the power minus kt c1 plus c2 plus ht c1 minus c2. This is become the solution. So we write here y is equal to e to the power minus kt a plus bt, where a is equal to c1 plus c2, b is equal to c1 minus c2. Sorry, h into h. Okay. So this expression shown us expression shows that this one is minus negative exponential over minus negative term. Obviously the displacement of the wave must be gradually decreases with respective time, as well as this term is also included, and such type of graph is like that. So this one is called critically damped motion. So you obviously think that what is the difference between the overdamped and the critically damped. So overdamped, actually the overdamped is actually like that. This one is called overdamped, and this one is the critical one. That because the negative term as well as the negative term and the positive term both are included in the case. So this one gradually decreases rapidly. This one, the critical one, when in the case of when the k square is equal to omega square, in that case the wave is gradually decreases than in the case of omega square, k square is greater than omega square. So this one is called overdamped and this one is called critically damped motion. Clear? So now we are going to the third one, in the case when the k square is less than omega square. So in that case obviously k square minus omega square is imaginary. So we can conclude that k square minus omega square is equal to root under k minus omega square minus k square is equal to minus root under minus 1 minus 1 into root under omega square minus k square. So we can rewrite I beta, let beta is equal to root under omega square minus k square. Now we put this one in a solution. Y is equal to c1 e to the power minus k plus I beta t plus c2 e to the power minus k minus I beta into t. Exponential of minus kt c1 e to the power minus I beta t plus c2 e to the power minus I beta t. So e to the power minus kt c1 cos beta t plus I sin beta t plus c2 cos beta t minus I sin beta t, because you know that e to the power I theta is equal to sin cos theta plus I sin theta, and e to the minus I theta is equal to cos theta minus I sin theta. Okay, so e to the power minus kt cos beta t c1 plus c2 plus I sin beta t c1 minus c2. When we take the c1 in a one side and c2 cos term in a one side and sin term in a another side, you get this type of solution. Okay, now e to the power minus kt a sin phi cos beta t plus a cos phi sin beta t. How it is coming? Let a sin phi is equal to c1 plus c2 and a cos phi is equal to c1 minus c2. Getting this constant value in term of phi, because we get phi is also a constant. Okay, now the solution is e to the minus kt sin beta t plus phi. Y is equal to a e to the power minus kt sin root under omega square minus k square into t plus phi. So this is the solution for the next one, and this one is called under damped motion. What is the graphical representation? This term shows that this is for the this term is responsible for the fall down of the vibration, and this term is responsible for the moving of the wave. So obviously the graphical representation of the under damped motion is like that. So this one under damped this one is called overdamped, and this one is critically damped vibration. So it is clear for everyone what is overdamped oscillation, what is underdamped oscillation, what is critically damped oscillation. Overdamped oscillation, the condition is k square is always greater than the omega square. Critically, k square must equal to the omega square, and it is obviously omega square is greater than the k square. Clear? Thank you.